This video is entirely sponsored by my supporters on Patreon, more on them later.
Hello there, welcome back to Beyond Ballistics. Today we're talking about rust removal. I'm sharing with you over 2 years of rust removing experiments and the final method that they led to that I'm quite satisfied with. If you're only here for the formula, you can find it at this timestamp, but I suggest you watch the whole thing to understand how to use it at the best of its potential and how it compares to other methods. What we're covering today is chemical rust removal, which is the best approach for restoring complex and stacked steel items. You could either go with a pre-made commercial solution or mix your own. The problem with commercial products is that there's a lot of variability between them and you won't know what the results will be until you try them out. Also, availability varies greatly from one country to the other, so what is available on the market for me probably will not be for most of you. What we want to do then is prepare our own mix from worldwide available chemicals. If you look online for a tutorial on how to remove rust, you'll be met with a plethora of remedies from groundless kitchen-made concoctions all the way to industrial strength acids. They all suck for one reason or another. The most common way of dissolving rust is to use an acid substance. Acids react with the oxides and hydroxides of iron that rust is composed of, transforming them into water-soluble salts that then simply dissolve in water, leaving behind solid metal. I tried most of them, either on or off camera, and none worked satisfactorily for restoration.
The most commonly used ones are hydrochloric, phosphoric, citric and oxalic acid. There's also vinegar, which is a 5% solution of acetic acid.
Even though some are definitely better than others, all acids have one big issue in common. They cause harm to the base metal, and that is due to the very low pH they work at. One way of dealing with this issue is adding a corrosion inhibitor to the acid that will shield the metal, letting the acid work almost exclusively on the rust. This is the way most commercial rust removers are made, usually consisting of inhibited phosphoric acid, a famous example being navel jelly. However, no inhibitor is 100% effective, they're often uncommon chemicals, and making a homemade mix that way didn't seem the best option to me. A different approach is to remove rust through chelation instead of acid attack. This is what a very famous commercial product claims to do, EvapoRust. I say claims to do because the actual composition is kept as a trade secret and nobody has a clue what's actually in it. I'm a wannabe chemist, so I'm not the right person to go in too much detail about the process, but in a nutshell, certain molecules have a high affinity for certain metals, so they envelop them, forming a large water-soluble complex that is then carried away by water. I experimented with EvapoRust extensively. It works at a good pace, does negligible damage to the base metal, and at the time, it was better than anything I'd ever tried. I was very happy with it. But my honeymoon with EvapoRust didn't last long. The product is incredibly expensive and doesn't last nearly as long as advertised on heavily rusted parts.
I had to find an affordable alternative to EvapoRust that worked on a similar principle. I searched far and wide and then settled on citrate ions. They also dissolve rust through chelation while being cheap and widely available.
After lots of testing, this is the mixture that I settled upon. To each liter of water, I'm adding 100 grams of citric acid and 40 grams of sodium carbonate, also known as washing soda. These two immediately react with each other, giving off carbon dioxide gas and forming mostly monosodium citrate and some disodium citrate salts.
Free citric acid is instead entirely used up in the reaction, but it turns out that the salts formed are so efficient at chelating iron that they work even better than the acid itself, but at a much higher pH, which is exactly what we want.
The pH rises from just over 1 of the citric acid alone to about 4. The pH scale being a logarithmic one, this means that the new solution is about 300 times less acidic than if I'd used citric acid alone. Just for comparison, my solution has now about the same acidity as tomato juice. The same result can be obtained using different amounts of sodium bicarbonate, also known as baking soda, or sodium hydroxide, also known as caustic soda.
For 1 liter of water and 100 grams of citric acid, you'll need either 40 grams of washing soda, as said, or 63 grams of baking soda, or 30 grams of caustic soda.
If you use the caustic one, you won't see any fizzing, but the end result will be the same. In any case, once the reaction is complete, the active ingredient of our rust removing solution is already there. We just want to add one more ingredient to act as surfactant. I'm using regular dish soap in somewhat arbitrary amounts, but I'm sure there's something better suited for the application, so if you're into the chemistry of detergents, feel free to experiment. If you haven't got a clue, better stick with dish soap. Now let's put it to the test against the only other contestant in its class, the overly expensive and boldly advertised EvapoRust. In the first test, I want to evaluate the two most important things: how much rust a given amount of solution can remove, and how fast it can do it. To keep things fair, I used the same amount of solution on a weight basis and added pieces of rusty sheet metal coming from the same plate to each of them, making sure each couple of metal samples weighted roughly the same, always putting the slightly heavier one in my solution to keep it at a slight disadvantage against EvapoRust. I then waited for the rust to be completely gone and recorded how long it took. On the first sample, I'd set my alarm after 1 hour, but I clearly underestimated the power of both products. They'd all finished long before then. So for the next couple, I kept an eye on them the whole time. They both finished after 30 minutes, so when both solutions are fresh, they act roughly at the same speed. But at the third sample, things started to change already. While the citrate solution took exactly the same as before, 30 minutes, EvapoRust started slowing down and getting darker in color. It took it 50 minutes to get the plate clean. And the time gap kept growing at each subsequent test. The fourth test lasted the same 30 minutes for the citrate, but 60 minutes for EvapoRust. The fifth took the same 30 minutes for the citrate, 80 minutes for EvapoRust. By the sixth test, EvapoRust was taking 3 times as long as when it was new, while the citrate mix kept performing at the best of its ability, finishing in about 35 minutes. After this, the EvapoRust only managed to clean 3 more samples, taking progressively longer, with the last one requiring about 10 hours. The citrate composition instead kept churning out clean samples taking no longer than 40 minutes, so I got impatient and dropped in a bunch of plates at the same time and kept doing that until I ran out of rusty sheet metal. The last batch took about 60 minutes and the solution was now dark green in color. It probably would have dissolved more, but I just didn't have any more. So here's how my solution compared to EvapoRust. The amounts of liquid used were exactly the same. To the right you have the plates cleaned by EvapoRust, to the left those cleaned with my solution. That's about 3 times as much for mine, and keep in mind that by the end of the testing EvapoRust was completely expended while the citrate composition was still active, and I had to stop because I'd run out of sheet metal. So as far as speed and capacity are concerned, my composition is a clear winner over EvapoRust. Another aspect where my solution really shines is cost. 1 kilo of citric acid at retail price is between 5 and 8 euros depending how much you buy. Washing soda is about 2 euro per kilo. This means that making 1 liter of solution will cost between 0.6 and 0.9 euros, less than $1. EvapoRust costs 11 times as much when bought in the 5 liter jug and about 9 times as much when bought in the 20 liter one. To put things in perspective, I paid 158 euro for this jug, which is the best price by litre I could get. The same amount of citrate solution would cost me about 15 euro, and it would process over 3 times as much rust in a shorter time. Not bad for a green on. This means my composition acts faster, lasts longer, and is massively cheaper than EvapoRust. But how does it compare regarding base metal damage? At the end of the day, that's the main selling point of EvapoRust. That's what we're about to find out. I've prepared 2 sets of tests, a closed vessel and an open vessel one. In the closed one, we want to evaluate the damage caused by the solution to the base metal in the absence of oxygen. So what I'm doing is I'm getting some clean samples of mild steel, measuring their weight at the beginning of the test and dropping them into 100 milliliters of each solution to be tested. The bottle is then squeezed to remove as much air as possible and closed. In this test, I'm trying my composition, marked as BB, pure citric acid at the same concentration, that is 10%, and a commercial rust remover containing about 25% inhibited phosphoric acid. In this test, we're giving EvapoRust the best advantage possible, that is, we're not testing it at all, and assuming the weight loss will be exactly 0, which is what the brand claims. The reason why I used a crushed bottle instead of a rigid container is that will also allow me to get a rough estimate on how much hydrogen is released, since the base metal loss would be proportional to that. The hydrogen evolution was however too slow to be measured this way, and only the pure citric acid bottle inflated noticeably. This is what the bottles look like after 22 days. For comparison, I also decided to test uninhibited phosphoric acid at the same concentration as the commercial one. The bottle in that case inflated completely after only 24 hours and had to be vented. In 41 hours, the steel plate had completely dissolved. So the inhibitors are really making a big difference here. Anyway, after 22 days, I took the samples out, rinsed and dried them, and then measured their weight again. Here are the results on a spreadsheet. Notice how the backyard composition caused a loss of thickness of the plate of only 0.4 microns in 24 hours, that is 0.2 microns per side, almost 10 times less than pure citric acid. This is important. It means that, as we expected, raising the pH led to a less aggressive solution. The commercial product did even better at 0.24 microns. About it, it's again interesting to note the terrific job done by the corrosion inhibitor. Phosphoric acid at the same concentration led to a loss of thickness of 275 microns, over 1000 more than the inhibited one. Unfortunately, in real life, we rarely have the option of derusting in the absence of oxygen, and most of the times we do it in open containers. So I'm repeating the test, but this time in open containers, allowing oxygen to interfere with the solution. This time I'm also testing EvapoRust. And I'm glad I did. After a few hours, the EvapoRust is changing color, meaning that some reaction is happening. But the samples were completely free of rust to begin with, so the only thing that could be reacting is the base metal itself. I checked the weight again after 5 days. The first thing to note is EvapoRust is in fact dissolving the base metal, at a rate of about 1 micron per day. The backyard solution seemed to be doing exactly the same, but since my reloading scale was struggling at measuring such small weight differences and was oscillating between 2.80 and 2.81, I again put it at a disadvantage choosing the lower reading. In that case, my solution is dissolving 1.4 microns per day, that is 0.7 microns per side, about a quarter of the thickness of an average bluing. That's tiny. Pure citric acid does over twice the damage in the same amount of time. So my solution acts faster on rust and slower on good metal, which is exactly what we need. The phosphoric acid commercial product is still performing nicely, although it lost the edge it had in the closed vessel test and is now performing slightly worse than the backyard solution. In lab testing, the backyard composition proved to be very promising. Let's see how it fares on a real rusty object. I've prepared 2 tubs containing the same amount of liquid. Both solutions started acting quite quickly. On mine, I saw a little bit of hydrogen bubbling out of the magazine. The amount is tiny, as confirmed by the closed vessel test. The reason we can see it now is the hole in the magazine is concentrating the hydrogen released by the whole internal surface into a small area. 48 hours later, both magazines were essentially free of rust. However, the EvapoRust by now was pitch black, and I know from experience that once this happens, the solution is practically dead. To be sure, I placed a rusty Garand clip in each solution. This confirmed that EvapoRust was completely spent, and after 12 hours the clip had barely changed. My solution instead returned a completely rust-free clip. I knew there was still plenty of rust dissolving power in the bath, so I decided to let it shine by dipping in this massive, heavily rusted magazine. Write in the comments if you know which gun it comes from. Much to my surprise, after 36 hours, the magazine was essentially rust-free. This once again proves the superior performance of my bath compared to EvapoRust. It costs 1/10 per litre and processes 3 times as much rust. That means that it's actually 30 times cheaper for a given amount of rust. It also acts faster on average. The only advantage of EvapoRust is in the slightly lower base metal attack and complete lack of hydrogen formation. Also, the surface left by the backyard solution looks a bit rougher than that of EvapoRust. But we have to be realistic. If you had to resort to chemical derusting, your surface is already way rougher than any of these solutions will ever make it. So my final advice is, if you're processing something extremely valuable that maybe only has rust in a few areas, spending between 10 and 30 times as much for EvapoRust and waiting the longer time it takes to act can make sense. In all other cases, I think that'd be a waste, but it's your choice, of course. Finally, let's talk about future improvements of the citrate solution. The main improvement that could be done is the addition of a corrosion inhibitor. As we saw in the case of phosphoric acid, corrosion inhibitors can make a huge difference. Adding a compatible one to the citrate mixture has the potential of further reducing base metal attack and surface roughness, eliminating the slight advantage EvapoRust still has in that regard. I know several plant extracts are efficient corrosion inhibitors, so that's where I'd look first. I'm already well behind schedule with my video making, as you know, so I'll leave this further testing to you. Let me know how you get on.
Once again, a huge thanks goes to my patrons, which as usual are all listed here. Thank you all for watching, subscribe if you'd like to see more, and I'll see you next time. Bye.